I can see the sunset, and in your eyes, and we ain't even done yet. Don't wanna go home yet. I spent the whole day with you, and we ain't even done yet. Don't you hate goodbyes? Rather say good morning than good night.
No, I can't even, which is good. A major factor in low lithium-ion battery recycling rates is that there's not really an economic incentive to do so. There are a bunch of reasons for this, but one of them is that the recycling process itself is too expensive. Talking to people at Umicore made me realize that battery pack disassembly is one of the major bottlenecks when it comes to the recycling process. So basically you have your battery pack and there are thousands of individual cells in there. If you want to recycle the pack, you typically need to disassemble it back into the individual cells. This is typically done manually. Beyond that, the individual cells are typically shredded, then they'll undergo a variety of different processes to extract the individual materials themselves. But there are a few reasons that pack-to-cell disassembly is done manually. The first one is that battery packs are optimized for efficiency, not disassembly. They're made in a way where they're screwed, welded, glued, wired up in a way that makes them super hard to disassemble. The second reason is that the batteries themselves are quite sensitive. So if you mishandle them, they could cause a fire or explode, which we obviously do not want. The third reason is that even if we look at just EV batteries, and there are a bunch of other applications beyond that, there are a ton of different manufacturers of EVs, and all of them are going to have a different battery pack design, which means that it's very hard to create a standardized disassembly process. So given that, I wanted to understand how battery packs are currently made to see why they're made that way, and if there's some modifications that we can make to the design that would then make them easier to disassemble. And if we could help that, then that would help to alleviate one of the major bottlenecks in the battery recycling process, and then help to make it more economically feasible. And I mean, what better way to learn something than to do it yourself? So the first step in building my own battery pack is to determine what parts I need. That actually means determining the requirements for my application. So to keep things simple, I picked a very arbitrary application, powering a motor. So that means my battery needs to be 24 volts and the capacity doesn't really matter. I was planning to buy my batteries on batteryhookup.com as per a friend's recommendation, and I ended up getting 18650 cells, which are the ones that Tesla uses in its Model S and Model X. I picked those ones largely because a lot of what I've been talking about has been related to EV battery packs, so I wanted to work with a battery that is actually used in EVs. And to clarify what 18650 is, basically it means that your cells are 18 millimeters wide on top and they're going to be 65 millimeters long. So another great thing about batteryhookup.com is that on their website they have a calculator that actually tells you how many cells you need given your application. So this will be based off the desired voltage and capacity for your application. To expand on this a bit more, if you connect cells in parallel, you can increase the capacity, but the voltage is going to stay the same. If you connect cells in series, you can increase the voltage, but the capacity is going to be the same. So let's say we want to increase both capacity and the voltage, as you typically would see in just about any battery pack. We would then get a rectangular battery pack with cells connected both in parallel and in series. In my case, my configuration was 7S4P, which basically means that I have 7 cells connected in series and 4 cells connected in parallel. This was to get me both the capacity and voltage I specified, given the nominal voltage and capacity of the 18650 cells that I was using. So aside from the batteries themselves, I also needed cell connectors, so little plastic snap pieces that will hold the cells in place, nickel sheets. I got ones with fuses on them for a little bit extra safety, and then also a battery management system suitable for your cell configuration. Mine again was 7S4P, so I just got a 7 series battery management system. And then in terms of tools, I needed a spot welder, soldering iron, and then of course, safety goggles and gloves.
No matter how I try, my body wants to know we cannot hide. I don't want this night to end. If only I could stop the sunrise, we can lay here all night. If only I could learn to freeze time and hold you forever. If only I had one more day.
So again, I'm making a 7S4P battery pack, which means I have 28 total cells. So using the cell connectors, I need to make 2 grids of 7x4 because these grids are going to be placed both on top and on the bottom of my battery cells to hold them in place. Next, I need to line up the cells so they are in the correct series/parallel configuration. So basically, in the rows, which are 4 cells wide, all of those cells are going to have the same terminal orientation because they're going to be connected in parallel. But down the columns, each cell is going to have the opposite terminal orientation because those ones are going to be connected in series. So after lining up the cells and double checking to make sure that everything was correct, because there could be short circuits if not, the next thing I needed to do was spot weld all the batteries together. So I did that using the nickel sheets and my spot weld. So on a short side note, I bought nickel in large sheets. You can also buy it in strips, but if you buy it in large sheets, make sure that you cut it into pieces that are 2 cells wide, because you only want to connect the negative and positive terminals on the adjacent cells. You don't want to connect everything. By connecting just the negative and positive terminals on the adjacent cells, you can get a kind of snake-wise current flow through your battery pack instead of just short-circuiting everything. So at first, I didn't realize this, and this is what happened. Basically, the problem with that is that I'm actually short-circuiting the batteries. That actually caused this to burn right there. It's like brown because it burnt, so it's not great. So after spot welding everything together and being extremely grateful that there was no fires and no explosions, I next wanted to check all the voltages of my battery and make sure that everything was what I was expecting. So do you remember how I said that by connecting things in parallel, you'll increase the capacity, and by connecting things in series, you can increase the voltage? You can use that to help you figure out what the voltages on various components should be. So the next step was going to be attaching my battery management system, or my BMS. A BMS is basically a piece of software that's going to sit on top of your battery pack, and its main job is to optimize the function of the battery. In my case, I have a fairly simple battery management system, and it's basically going to help prevent the battery from exploding. So it's basically going to help prevent overcharging, over discharging. It's going to help balance the voltage across the cells, and it's also going to help prevent short circuits. So again, this needs to be specific to your configuration, and also it's important to look into how the wires are supposed to be attached to your battery pack. So with mine, the white wires ended up being connected on the negative terminal of that cell. So for example, if it was the 4th white wire, that would be connected to the negative terminal of the 4th cell row. And then I used the soldering iron to attach these lead wires from the battery management system to the nickel sheets that I had soldered on earlier. An important little side note here as well, when I was soldering on the nickel, I left the outermost row unsoldered because I didn't want much heat to go into the battery itself, just as like a safety precaution. So I attached the BMS leads via the soldering iron, and then I went back and spot welded the final row of the nickel. The final thing I needed to do here was to connect the battery to the charger and the load, which would mean I could actually use it. In my case, the load was a motor. So this setup is going to vary drastically depending on your application, but I decided to use a SPTT switch, which basically means that it has 1 input and then 3 outputs, so 1, 2, and 3. And I wanted to use that switch because then I could control whether the battery was charging, discharging, or off. To go through the connections briefly, I connected the positive terminal of the overall pack to the input of the switch. And then I connected the negative terminal overall to the pack, which is this black wire here. And that's connected into the BMS, and it goes to the B negative terminal. So that I didn't have to do anything, that was already connected. The first position of the switch connects to the charger positive. So this would connect to my charger. And this is the first position of the switch here. So I've got a barrel jack alligator clip adapter in order to make that connection. And then I have the second output of my switch was connected to the motor positive. And then third position represented off, that doesn't have any connections. And then the C minus terminal, which is in here, would be connected to this alligator clip, which is the charger negative. I have it off right now just because I don't want the battery charging. And then the final connection was the motor negative being connected to the B negative terminal, which is right there. So the hardest thing that I can tell about this pack from having built it when it comes to disassembly is the spot welds. These things do not seem like they're going anywhere, and I actually don't know how these are disassembled in actual recycling facilities. But again, when it comes to an actual Tesla pack, there's a lot of other components that I just didn't include in this one. So there's a thermal management system. The battery management system is much more complicated. There's an external casing on the battery pack with like a bunch of screws. There's also probably some sort of insulation around each individual cell to help prevent it from being like shaken up from impacts of the vehicle and whatnot. But in short, things would probably be a lot more complicated in an actual Tesla battery. But this one did give me a good understanding of like the basics and the fundamentals of the things that are included in just about every battery pack. But with that, I hope you enjoyed learning about how battery packs are made. And I also hope that you were as grateful as I am that nothing exploded or caught on fire. But with that, I will see you in the next one.